Welcome to Elementary Calculus, Chapter 3, Section 4, where we're going to talk about the definition of a derivative. Things are starting to get good now because we're getting closer and closer to being able to take some shortcuts around the limit process that has been an integral part of the exploration that we've been doing so far of so many of these functions. And the definition of a derivative is going to very much involve the tangent line, or the tangent to a curve. And the process of finding a tangent to a curve can very well be illustrated with, or is very well illustrated by this diagram. And what's happening here is we have fixed a point R, which is sort of toward the bottom of this curve. And with this fixed point R, we're taking a second point, starting out with S1, and we draw this line that goes through R and through the point S1, and that's called a secant line because it crosses our graph at more than one point. And if we knew the coordinates of those 2 points, R and S1, we could calculate the slope of that secant line. And if we take S1 and we lower it down so that it's closer to point R, we move it to here, and we draw a line through those 2 points, we could find the slope of that line. And if we continue bringing this additional point closer and closer to point R, the slope of the secant line continues to get closer and closer, or more and more similar to the slope of the tangent line. And so the trick here is going to be how close can we get our secondary point to point R so that the slope of the secant line becomes almost identical to the slope of the tangent line. And we're going to be doing that using limits combined with the difference quotient. So the slope of the tangent line can be found by using the difference quotient and then taking the limit as h approaches 0. And what that's going to do is, here's the tricky part of the explanation. Point R has an x-coordinate, and this sort of supplemental point that we've been using, let's use S4, this point also has an x-coordinate. And as we move S4 closer and closer to point R, the difference between the x-coordinates is going to become smaller and smaller. And by the difference in the x-coordinates, I mean the coordinate x-coordinate of S4 minus the x-coordinate of point R. Now if point R has an x-coordinate of A, and the difference between the x-coordinate of point R and the x-coordinate of point S4, if the difference between those two x-coordinates is h, if we make h smaller and smaller, then the difference between the x-coordinates is smaller and smaller, and therefore S4 is closer and closer to point R. So that's what the A and the H values are that you're seeing in the difference quotient toward the bottom of your screen, where it says A plus H. As we send H off towards 0, the difference between those x-coordinates is getting smaller and smaller because H is getting smaller and smaller. Okay. Now, remember please that f of a plus h represents a y value. That's the y value of our secondary point. And f of a is the y-coordinate of point R. So what you're seeing in the numerator here is y2 minus y1. So this looks a lot like the calculation of slope. Now if the difference between our x values is h, bear with me one moment here, then the x-coordinate of our secondary point is the x-coordinate of point R plus that difference of h. So again, this is the x-coordinate of our secondary point. In this example, we're calling it S4. So this is an x value, a is an x value, and we're going to call this x2, and this is going to be x1. And in the denominator, toward the bottom of your screen, if we complete the idea of calculating slope by putting x2 minus x1 into the denominator, and then we come back up here and we look at these two x coordinates that we were just talking about, x2 is a plus h, and we subtract x1, which is lowercase a, this simplifies to just h. So at the bottom of your screen, right in the middle, x2 minus x1 is being denoted as h, because h is the result of doing that subtraction process. It is the difference in our x values, or the change in x. Again, as we apply the limit and our h value gets closer and closer to 0, the slope that we're calculating in this process will get closer and closer to the slope of our tangent line. When we were still working with a secant line in that graph, the slope that we were calculating could be referred to as the average rate of change. But as those 2 points get closer and closer to each other, and as we send h off to 0, and the slope of the secant line essentially becomes the slope of the tangent line, that slope, the slope of the tangent line, is our instantaneous rate of change. And that is a very valuable number to have, especially in business applications. And we will see an application problem toward the end of these notes. So here we could estimate the slope of our tangent line by using the point that was given to us and then trying to find another convenient value. Maybe, I don't know if I like that one. I don't know if I love that one. That one's a little too high. So maybe this one is, maybe this one's 3, 7. So we could use, 7, 3. We could try to solve this graphically and calculate our slope that way. So m would equal y2 minus y1 over x2 minus x1, which in this case, let's use this as our second point and 3, 1 as our first point. So our second y value is a 3, our first y value was a 1, our second x coordinate was a 7, our first x coordinate was a 3, so we have 2 over 4, which is equal to 1/2. And I would agree with that. That line doesn't look like it's all that steep, so that one's got a slope of approximately 1/2. It would be much more helpful if we actually knew the equation of the curve, and then we could very precisely find the slope of that tangent line. Now, when we go through this process of evaluating the limit of the difference quotient, without plugging in a number, so you see that we're just using a generic x value here, the result of this process is going to be a new function called the derivative. And the derivative is denoted as f prime of x. F prime of x. And the prime looks sort of like a straight apostrophe. You can see a good example of it here. It's this thing. It's not quite an apostrophe. It's just a little mark. And that's read f prime of x. In order to evaluate the derivative of a function at a particular x value, our original function has to satisfy some conditions, and we're going to talk about those as we go along, but certainly one of the conditions is that it must be differentiable, and there are some nuances to that restriction. In order for our function to be differentiable, in order for us to find the derivative, this limit has to exist. So as we're approaching that point R that we saw in the initial illustration, as we approach from the left and as we approach from the right, we must be approaching the same limit value, capital L, as we have seen it many times, and the function has to be defined at that point. So this box here is just showing the transition of what happens as we apply the limit to the difference quotient. The slope of a secant line becomes the slope of a tangent line. Average rate of change becomes the instantaneous rate of change. Average velocity becomes instantaneous velocity, and as applies most specifically to the business world, your average rate of change in cost or revenue or profit is going to become the marginal cost or revenue or profit. And again, we'll see an example of that in a little bit. The 4 simple steps, if you're the kind of person who likes an outline of the process, this would be valuable to you, and you might want to write this down. The steps for finding the derivative are first to evaluate the first component that we see in the difference quotient, which would be f of x plus h. And then we're going to subtract the original function from f of x plus h. We'll simplify that, and then we'll take that entire expression and we'll divide it by h. And if all goes well, that's going to simplify nicely. And then we'll introduce these 2 additional pieces of notation. We'll take the limit as h approaches 0, and the result of evaluating that limit will be a new function, which is our first derivative. So let's give it a shot. Example 2 is a 2-part question. First, we're going to find the first derivative, and then we'll evaluate that first derivative at a given x value of 4. So step 1 tells us to evaluate f of x plus h. In this case, we're going to take the x plus h and plug it in, replacing all of our x's with an x plus h. So this will equal -1 over x plus h plus 6. And then we need to calculate f of x plus h, but also subtracting our original function, f of x. So that is -1 over x plus h plus 6, and then we have to subtract -1 over x plus 6. In order to do this subtraction, of course, we're going to need to find a common denominator. So I am going to multiply my first fraction by x plus 6 over x plus 6, and I'll multiply my second fraction by x plus h plus 6 over x plus h plus 6. The result of that multiplication will be -1 times that introduction of the x plus 6, and then we have a double negative that's happening here. We're subtracting a negative, so I'm going to turn that into a plus sign, and then the 1 times the x plus h plus 6 gives us those subsequent three terms, and then we're dividing all of that by our common denominator, x plus h plus 6 times x plus 6. And then we can simplify this a little bit, and that is one of the instructions in that second part. So I, in my numerator, have negative x minus 6 plus x plus h plus 6. And that's still all being divided by our common denominator. Still has those same two factors in it. And when we simplify or combine like terms, CLT for combined like terms in our numerator, the negative x will cancel out with the plus x. The minus 6 is going to cancel with the plus 6, and we will be left with only an h in our numerator divided by our two factors. Let's actually write them in this time. X plus h plus 6 times x plus 6. So that's the second step in the process. And then the next thing we need to do is actually build the difference quotient. And I'm going to introduce the limit. I'm going to do steps 3 and 4 all at the same time here because I'm getting a little bit short on space down here. The first derivative of our function is equal to the limit as h approaches 0 applied to a function that's a little bit gnarly looking. We need to take the expression that we just wrote out, so I'm copy and pasting this into here. And then we need to divide all of that by h in accordance with the difference quotient. We could think of this, if we wanted to, as h over 1, and then we could implement keep, change, flip, which would result in us multiplying the numerator by 1 over h. And when we simplify that, we have to bring in the limit along with us as h approaches 0. And when those h's cancel, we're left with 1 over x plus h plus 6 times x plus 6. In our denominator, we have the product of two polynomials, both of which are continuous everywhere. Our numerator is a constant value, which is continuous on all real numbers. So we can evaluate this limit using direct substitution. So let's plug in an h value of 0 and finally have our first derivative. I'm going to move my equal sign back over here to the left. There we go. So this equals 1 over x plus 6 times x plus 6. And we could write that maybe even more concisely as 1 over x plus 6 quantity squared. So that is your first derivative, and if you like to circle your final answers or put boxes around your final answer, you could do that. You could write equals f prime of x there. That's also true. And then the next thing we are asked to do is to evaluate our first derivative when x equals 4. So f prime of 4 equals 1 over 4 plus 6 quantity squared, which equals 1 over 100. And you have just found your first derivative, which doesn't seem all that exciting right now, but maybe one day you'll look back on your first exposure to calculus at the college level and you'll remember having evaluated or found your first derivative using the limit process. And eventually we're going to be able to do this process much faster. But having that conceptual understanding that what's happening behind the scenes is fixing that first point of R and then bringing in this other point and getting it closer and closer and closer so that your secant line is more closely approximating the actual instantaneous rate of change. It's important to have that behind the scenes understanding. And in the real world, in the business world, in the world of economics and finance, these kinds of approximations are being used maybe literally all the time. There are computers that are generating these approximations in order to do forecasting, and it's happening every microsecond. So there's another example here where we could go through that same process and evaluate f prime of 5, but the process is going to be the same. But we'll do it again in this next example, except we're going to roll in an additional aspect where we're being asked to find the equation of this tangent line. So what we did in the previous process is we found the slope of the tangent line, the instantaneous rate of change. And then, in order to make a forecast about what's going to happen in the future, potentially, we will need an equation, in this case a linear equation, that would help us project forward in time. We're being reminded of the point slope form for the equation of a line. This essentially says y minus y1 equals m times x minus x1. All right, so that's what those represent based on how we originally saw point slope form. So let's try to find the equation of the tangent line in example 3. The first thing we need to do is determine the slope of the tangent line, and in order to determine the slope of the tangent line at a particular x value, we're going to need a function that will generate slopes of tangent lines, and that function is called the first derivative. So let's find the first derivative. F prime equals, I'm doing it all at once here, f prime of x equals the limit as h approaches 0 of f of x minus h, right? Don't forget. Let's go all the way to the top. So I said f of x minus h. F of x plus h, because we're going to start at that point R and then move to the right a little bit. So f of x plus h, so we're plugging in an x plus h in place of x. So that is x plus h, which we have to raise to the third power. And then, I didn't quite orient that stuff the way that I wanted to. X plus h to the third power divided by 2 minus the original function, f of x, which is x to the third over 2, and then we have to divide all of that by h. So again, in your notes, if you want to indicate to yourself that this is f of x plus h. This is f of x. There's the h. That's all. Those are the three components of the difference quotient. And then now we have to simplify this as much as possible and then apply the limit. The first numerator that you're seeing there, x plus h in parentheses to the third power, if we expand that, if we were to FOIL it and then FOIL again and combine like terms, we will get x to the third plus x squared times h plus x times h squared plus h to the third. And then we have to subtract our x to the third power. Now those were the two numerators that we were seeing over here. The first numerator and the second numerator. Both of those numerators were being divided by 2. They already had a common denominator. So I'm going to divide all of that by the common denominator of 2. And then we have to take this entire fraction and divide it by h. Or multiply it by 1 over h, because division is the same thing as multiplying by the reciprocal. So I'm going to now do my simplification process. The only simplifying that happens here is that this positive x to the third cancels out with this negative x to the third. And I'm also going to introduce or change this division by h. I'm going to turn that into multiplication by 1 over h. Let's see what we get. X squared h is still there, plus the x times h squared is still there, plus the h to the third is still there. And then we're taking this and we're dividing it all by 2, and we're multiplying it by 1 over h instead of dividing it by h. And the result is that h is going to appear in the denominator with the 2, or if you're comfortable with it, you can cross-cancel, as I've heard some students refer to it. What a lot of people forget to do is they forget that they have to distribute their division. This division by h has to divide into all 3 terms in our numerator. And the result of that will be the h squared is still there, but the x squared is still there, but the h canceled out, plus x times h to the first power only, because one of those h squareds canceled out, plus h squared, because one of these 3 multiples of h canceled out with the 1 in the denominator. And our denominator of 2 is still there. And what I've done, which is something that I do a lot and that you're probably going to do a lot too because we're not used to doing it over and over again, is I didn't write my limit statement. We have to bring that along with us the whole time. So I'm going to erase and come back here and put in my limit as h approaches 0. Put my equal sign back there, and then maybe I can take this other equal sign, move it to the left a little bit, and squeeze my limit in there. Limit as h goes to 0. The size of my limit statement keeps going towards 0, keeps getting smaller and smaller. Look, it's huge here, and then it's medium-sized here, and now it's kind of small in here. In our numerator, we have a polynomial, which is continuous everywhere, so I can solve my numerator by direct substitution. The denominator is a constant value, so it's going to stay the same, and we find that our first derivative is equal to x squared over 2. That happened because the second term in our numerator became a 0 because h went to 0 by direct substitution, and our third term in the numerator also became a 0 because of direct substitution. So this is your f prime of x. This is your first derivative. So if you'd like to put a box around that, you've earned the right to do that. And then the question also asks us to find the equation of the tangent line to the curve when x equals 2. So the slope of the tangent line at the point when x equals 2. Slope of tangent at the point on f of x where x equals 2 is f prime of 2. So we take the x coordinate and we plug it into our derivative, and that will help us generate the instantaneous rate of change, in other words, the slope of the tangent line. So that is equal to, we'll take the 2 and plug it into the numerator, square it, Divide by the 2 in the denominator, and we get 2. And that's going to be our m value. That's the slope of the tangent. And now we need to actually find the slope of the tangent. Or sorry, we need to find the equation of the tangent line. And we're going to do that using point-slope form. Do we know what the slope of the tangent line is? Yes, we just calculated that. It's 2. Do we know the coordinates of the point on the curve where we're going to be drawing this tangent line? And the answer is no, not totally. We know the x-coordinate of that point, but we need the y-coordinate also. So I'm going to write down need y-coordinate on our original function f of x, where x equals 2. And how am I supposed to find that y-coordinate? I'm going to take my x value and plug it into my original function. So let's do that. F of 2 is, where's our original function? In the top right corner of the screen there's your original function, x to the third over 2. Something's wrong. I made a mistake. It's a little one, easily corrected. Let me put it in the top right-hand corner of your screen for you. Do you see where I circled x to the third power? I circled it in red. And then we went from there down to the next line of our work, and I wrote x squared, and that was a mistake. We need to change that to say x to the third. Where did it go? There it is. I'm going to put it in red, so that's now x to the third. That was a correction. And then was that a mistake? Oh, it wasn't, because we canceled out the x to the third. That's what was happening in there. So that's okay. Sorry about that. Change that 3 back to a 2. I was trying to nip that in the bud before it became a real issue. All right, let me just do a quick double check here. X to the third. That's what the mistake is. Oh my gosh. I'm trying to think about too many things and talk about too many things all at the same time. So we made a mistake by omission. I made a mistake by omission. The thing that's missing is in the top right corner of your screen, where I circled that x to the third power, to the right of it, it says plus x squared h. It should say plus 3x squared h. And then to the right of that, it says plus xh squared. It should say plus 3xh squared. We need to take those 3's with us from there down onto our next line of work. So we're coming down here, and this should say 3x squared h. And from the top right corner of your screen, come down also, and this should say plus 3xh squared. And then bring those 3's to the right with you. This should now say 3x squared, and what I circled in purple should say plus 3xh. Very sorry about that. Plus 3xh, it says now. And the final implication of that, when we evaluated the limit, these two terms do still become zeros because the h value got plugged in as a 0, but the 3x squared needs to come down and be part of our final answer so that it says 3x squared over 2. Then we have to bring that 3 with us onto the next line, when we're evaluating f prime at 2. So this needs to have 3 in front of it. And 3 times 2 would make 6, which means that this 2 right here now needs to be a 6. That was a close one. Okay, let's carry on. So we do still need the y-coordinate on our original function f of x, where x equals 2, and in order to calculate that, we are still going to take an x value of 2 and plug it into our original function. Our original function again is x to the third divided by 2. So we have our 2 to the third power divided by 2. And when we simplify, that's equal to 4. Which means that x1, y1, the point that we're going to be using in point slope form, we had an input value of 2 and an output value of 4 in our original function. So that's the point on our original function where we're going to be finding the equation of the tangent line. The equation of the tangent line, we're going to find that using y minus y1, or you can call it f of x1, equals our slope m, or you could call it f prime of x1, times y minus y1 equals m times the quantity of x minus x1. It's a lot. There's a lot of business going on right there. But we know what the necessary values are in order to complete this. We know that f of x1, let's actually write out one more step. So we have y minus our y value of 4 that we calculated over here. That's the 4 that I just wrote in, equals, we know what the slope of our tangent line is at that particular point. We calculated that to be 6. That's this 6 up here. F prime of 2. I don't like it. It was all correct, but I don't like it. Let's write in one, let's make this one additional step. Let's have this say f of 2, because that's the x coordinate that we're working with, equals f prime of 2 times x minus, and we know that our x1 value is 2. So if you wanted to, pardon the 2, let's take it from the bottom and work our way up. This 2 right here is the same as this 2, is the same as this 2, is the same as this 2, which is the same as this 2, and this one, and really it's the same as this one, and this one, and finally this one in the top right corner. That's the 2 that we just brought down along through this whole process with us. That 2 is really driving our final answer in combination with our original function. So we used the limit process to find f prime of x, which is our first derivative. That's right here, f prime of x. We did all of that without the x value of 2. We just used our original function and the limits in order to find the first derivative. Then we found the slope of our tangent line. Oh, I found another 2. It's off screen. There it is on the right hand side of your screen, right in the middle. There's that x value of 2 again. So we found the slope of the tangent line when x equals 2. So now we're incorporating the 2 and we're mixing it in with our first derivative statement. We're evaluating the first derivative at x equals 2, and we got this m value of 6. So now we have a slope, m equals 6. We have an x coordinate, x equals 2, but we need the corresponding y value. So we found that y value to be 4, and we figured out that y value by taking the x value of 2. Oops, I found another x value. There's that x equals 2 again. We found the y coordinate of 4 by taking 2 and plugging it into our original function, f of x. So now we have an x coordinate of 2, a y coordinate of 4, and a slope of 6. Those three numbers are what we are plugging into point slope form. And here's the equation, very generic equation for point slope form, except instead of saying y1, we're saying f of x1, and instead of saying m, we're saying f prime of x1. And now what I'm doing is I'm plugging in what I know to be x1. We said that our x value is a 2, so I've replaced x1 with a 2. Now I'm going to make another pass through this equation. What is f of 2? We know what f of 2 is. F of 2, this f of 2, we processed that. It turned out to be a 4. That's a y coordinate. So I'm going to replace f of 2 with a 4 equals, now this says f prime of 2. We know that f prime of 2 is our first derivative evaluated at an x value of 2. That turned out to be 6. So let's get the 6 in there as our slope, times x minus, and that 2 was already there. That was our x coordinate of 2. This is the slope of the tangent line if we leave it in point slope form. We could convert this into slope intercept form by distributing our multiplication by 6 and then adding 4 to both sides. If we do that, we get y equals 6x minus 12 plus 4 is minus 8. This is slope intercept form. And that's a great way to present your final answer. I would not write this as f of x equals, because we've already used the name f as one of our functions. That was our original function. The slope of this tangent line equation that we just wrote, if you want to write it using function notation, call it g of x. Call it tangent line of x. Something. Give it a different name other than f. And as I recall, oh, that was it. All we had to do was find the equation of the tangent line when x equaled 2, and there it is. This is clearly a multi-part problem. So be patient with yourself, stay organized, try to label the different components of the process. I've already talked through it a couple of times, but this was, I bracketed it on the left there, that was finding the first derivative. The next two lines were using the first derivative and the given x value in order to find the slope of the tangent line. The next two lines were using the x value of 2 and the original function to find the corresponding y coordinate. And then the last part of the process, these last 5 lines, were the actual creation of the equation of the tangent line. You've got your work cut out for you on these, all right? This is a very typical and traditional problem. Am I always, all right, so we're going to change gears and go conceptual for a moment. The existence of the derivative. Can I always find a derivative? Does a function always have a derivative? Most functions that you work with, especially at the beginning, are going to have a derivative. But the question is, are you going to be able to evaluate the derivative at all of the various x values that are present on a graph? And the answer to that question is no. You're seeing some illustrations here. For example, here it says no tangent line possible. And that's because the graph comes to a sharp point at x1 and x2. So sometimes there's just no way to figure out what the tangent value is. Here at x3, we're seeing a jump discontinuity. You just try to draw yourself a tangent line right there. Tell me what that's going to look like. It's not happening. You certainly couldn't evaluate that because as x approaches x3, the limit doesn't exist, because the limit as you approach from the right would not equal the limit as you approach from the left. So that limit doesn't even exist. Here, there's an asymptote at x equals 4, which means that our function's not even defined at x equals 4. So I can't find the equation for a tangent line, nor can I even find the slope of the tangent line to a function at x4 if the function doesn't even exist at x4. So that one's out. So if there's a vertical asymptote, we can skip over that. The function will not be differentiable at a point where you have a vertical asymptote. And it does happen every once in a while, like you're seeing at x5, where the slope of the tangent line would be undefined because the tangent line is a vertical line. And as you might recall, vertical lines have an undefined slope. So that one would be problematic. And again, if our function's not defined somewhere, as is the case with x6, we will find the function is not differentiable. We can't find the rate of change at a point if the point does not exist. So the existence of derivative, or of the derivative exists if all of these first 3 conditions are satisfied. The function has to be continuous, which means it doesn't have a hole or an asymptote. The function has to be smooth, which means it can't come to a sharp corner like we saw with x1 and x2. And the function cannot have a vertical tangent line because the slope of the tangent line would be undefined. And you can approach this inspection of a function or of a graph sort of from the other side by saying, when does the derivative not exist? Well, it's not going to exist if the function's discontinuous, hole or asymptote, if it has a sharp corner, or if it has a vertical tangent line. Just a different way to phrase the first 3. Let's look at this graph quickly and see, is there a point where this function is not differentiable? And the answer is when x equals 0, our function is not differentiable because it's not smooth, which is a technical term. What about the next graph? When is this function not differentiable? It's not differentiable, again, when x equals 0, but for a different reason. Here it's not differentiable because we have a jump discontinuity, and there's a hole here and a hole here, so our function's not even defined for x equals 0. So we definitely could not find or evaluate the derivative there. And this function, when is this function not differentiable? Here it's not differentiable at 0 again, but for a different reason still. Here it's not differentiable because when x equals 0 or at x equals 0, we have a vertical asymptote. So just some visual examples of some of those conditions that we talked about in that previous orange box right here, or gray box, or sand-colored box maybe. And then the last thing I want to look at with you is an applied problem from business and economics, where we're looking at the profit from the expenditure of X $1,000. So if X is equal to 1, we're talking about $1,000. These expenditures are being made on advertising, and the profit from this expenditure is given by this function, p of x equals 1040 plus 25x minus 3x squared. And we want to find the marginal profit when the expenditure is $9,000. So your task here is to find the first derivative, which would be the marginal profit function. Instead of f prime, that's going to be p prime. And then we'll evaluate p prime at 9,000, or just at 9, since x represents thousands of dollars. So let's, as quickly as we can, find p prime. P prime of x equals the limit as h approaches 0 of, and then we need p of x plus h minus p of x, that's y2 minus y1, all divided by h, which is x2 minus x1. Let's plug in the x plus h into our function. So we have the 1040 plus 25 times x plus h minus 3 times x plus h quantity squared. And then we have to subtract our original function, which is never going to fit the way that I'm writing it. So I'm gonna back up. I'm going to take all this stuff and just going to move it down to the next line so that it'll fit. So I'm again plugging x plus h into my function. We have the original 1040 plus 25 times our new x value of x plus h minus 3 times the x plus h quantity squared, and then we have to subtract the entirety of the original function, which, very important here, put the original function in parentheses. So we're subtracting the 1040 plus 25x minus 3x squared, and then we're going to take all of it and divide it by h. And then we'll bring that limit statement with us. We'll keep trying to remember to do that. Here we are. What's going to happen here is this positive 1040 is going to cancel out with this subtracting of 1040. Oh, we don't want to do that yet. I'm jumping the gun. We need to do some arithmetic first. We have to distribute this multiplication by 25. We have to FOIL this x plus h quantity squared, and then we have to distribute multiplication by -3. I was getting excited. We've got some more work to do. Keeping the 1040 plus 25x plus 25h, so I'm distributing, minus 3 times, if we FOIL this and combine like terms, we get x squared plus 2xh plus h squared. That's the result of doing x plus h times x plus h, FOILing and combining like terms. Then let's distribute the minus sign, so minus 1040 minus 25x plus 3x squared because of the double negative. And we're going to take all of this and divide it by h one of these days. I keep trying to do it too early, but we'll be patient. Equals still the limit as h goes to 0. We have not evaluated the limit yet. Now I'm going to distribute my multiplication by -3 to these three terms. Oh, careful. This should say minus 6xh minus 3h squared. And then everything after that is the same. Minus 1040 minus 25x plus 3x squared. And we are still all being divided by h. What a mess. Now that we have done all of our FOILing and distributing, now we can combine like terms. There is a positive 1040, and over here to the right of center is a minus 1040. At the left we have a plus 25x, and to the right we have a minus 25x. And to the left just to the left of center we have a minus 3x squared. And all the way to the right, we have a plus 3x squared. You'll notice that at the very top of your screen, where it says minus p of x, and then on the next line, it says minus, and then we put what p of x is, and there's 3 terms in there. We distributed that minus sign, and we got these 3 terms. And then look what happened in this most recent step. All 3 of those terms canceled out with 3 terms from earlier in the statement. That should happen every time you evaluate the difference quotient like this. If you're evaluating the difference quotient and you don't cancel out all of those terms that were in your original function, like I've highlighted here, something has gone wrong. Okay? I caught myself on a couple of earlier mistakes, and that's because I know what to look for, and because honestly, I can do this process in my head, so before I even started doing it, I knew what the answer was going to be. You'll get to the point where you could do it in your head also. I promise. I'm going to get you to that point. So that's how it is that I'm going about checking my work, and how I know that I've made some little oversights as we're going along. So this is a good thing for you to know, because it'll help you check your own work as you're going along. That's going to happen every time. Okay, let's write down what we have left. Keeping the limit statement. This is a very labor-intensive process, isn't it? But it's not heavy arithmetic, right? The math in here isn't crazy. It's just kind of an organizational pain. We have the 25h still, and we have a minus 6xh. A sharp pencil is obviously, or a good pen is a good thing to have for this process, and I highly recommend mechanical pencil, because it's going to stay sharp all the time, and it's erasable. And as you can see, everybody makes mistakes, even me. So, did I leave anything out? Nope, I've got everything. I've got my 3 remaining terms. I'm still dividing by h. I brought my limit statement with me. And now we're going to simplify or reduce. And you must distribute your division. Always have to distribute division to all of your terms in the numerator. So the h from our denominator is going to cancel out this h, and it's going to cancel out this h, and it's going to cancel out one of those factors of h. And once we do that simplifying, I'm going to move over to the right here just to keep using all of my available space. We have no denominator anymore. We have a 25 minus 6x minus 3h. And now, finally, because you've been excited about this part, we can evaluate the limit. And inside of our square brackets here, we have a polynomial, and that means that we can evaluate our limit using direct substitution. So our first derivative of our function that we've been working with here is 25 minus 6x, because the 3h turned into a 0 and disappeared. And now I'm going to go up and glance at this, and yep, that is the correct first derivative. Now this is your, so this was all about profit from spending thousands of dollars on advertising. So this is a profit equation, except now it's no longer a profit equation. In fact, this entire time it's been p prime of x, and p prime is the marginal profit function. So if you'd like to put a little note right here that says equals p prime of x, which is my marginal profit function, you might want to put that note into your notes. And then we're going to evaluate our marginal profit function when our expenditures are $9,000. So let's evaluate p prime of 9. So we have 25 minus 6 times 9. 25 minus 6 times 9. That's not looking so good. That is 25 minus 6 times 9 is 54. As far as profit's concerned, I'm not loving that as far as a profit number. And because I'm not a fan of arithmetic, I never want to make a mistake on the easy stuff. So I do 25 minus 54 in my calculator, and I get negative 29. $1,000. That's not good. I just spent $9,000 on advertising, and I ended up realizing a profit that's negative, and it's negative big. There was one other part of this question. It said, should the firm increase the expenditure? Now we had an expenditure of $9,000, and that was our X value. And here is where the X value went into our marginal profit function. If I make that number larger, then I'm going to end up subtracting an even larger number. Does that sound like a good idea? I would say no. I definitely don't want to increase my expenditure on advertising because it's going to make my marginal profit even lower. In fact, this number right here, if we had an expenditure of $4,000 on advertising, then 6 times 4 would be 24. This arithmetic I can do in my head. 25 minus 24 would be 1. So it appears just based on these functions and knowing and nothing else about the bigger picture, that if we keep our advertising expenditures under $4,000, that we're going to still realize a marginal profit. Could I maximize my marginal profit by reducing my advertising expenditures to 0? Just based on these functions that we're looking at here, it looks like the answer is yes, but we know that there is much more involved in the bigger picture in terms of trying to make a determination like that. No advertising, I don't think anyone's buying. I think your profit's going to be even more negative if you had a 0 advertising budget. So just remember that this is just a little piece of the puzzle. Remember that this is a very detail-oriented process, that you need to be patient with yourself, and as you go through and you do practice problems and homework problems, don't hesitate to ask additional problems about the process, conceptual questions or process-oriented questions. Keep up on your algebra skills because those are obviously necessary here, and I'll see you soon. Thanks.